Good. All right, let's get going. So let's finish this trip to the outer planet and back. So I'm going to refresh what we have done last time. We said that if we're going, and again, this is all reversible. You can go from the, that's exactly what we're going to do, from a bigger circle to a smaller one. It doesn't really matter. We said, okay, if we want to reach planet 2, leaving planet 1 on this Hohmann or cruise half ellipse, we need to make sure that planet 2 is ahead at the moment where you're giving this delta V here, because it's moving slower, and we said that that phi0 had to satisfy this simple relationship, pi minus the angular velocity of planet 2 on its orbit, the time of flight on that half ellipse, which we have computed last time. And we said that this also happens so many times because, you know, things repeat themselves. Everything is periodic there. You have two angular velocities, two oscillations if you want, on two circles. The synodic period, you can show it's T1, T2 over the absolute value of T1 minus T2. And one of the examples in the book shows you how much time you have to wait, we're talking about years, before a case like this repeats itself between the Earth and Mars. What else did we say? Okay, we said, well, at the end of this transfer flight on the green trajectory, the phase angle, which we called phase angle final, it's going to be phi0 plus n2 minus n1 T12, and I'm going to repeat the steps. This is pi minus n1 T12, which we have proven this being to be negative, right? So, which makes sense. Planet 1 is moving faster, so at the end of this, when the spacecraft reaches planet 2 right here, planet 1 has actually gone ahead of planet 1 ahead of 2 of that additional of this angle phi final. And again, we define some line that we call the line of Abs, even though it doesn't exist, the time zero from which we measure the true anomalies, and we define the phase angle as theta 2 minus theta 1. So if 1 is ahead, it's a negative value. Okay? So that's what you do. Still, we're looking at things from the sun's perspective. This is all heliocentric. What is happening in the vicinity of these two planets, we're just ignoring it. We're assuming just that we leave one and we reach the other one like a classical Hohmann transfer, nothing special. The problem is that you have to time them correctly so that something is there when you arrive, in this case at planet 2, for example. And so it's all a matter of waiting for that phi0 and knowing how often you can get it, how much you have to wait if you miss that window. And that's all for the departure. And then we'll focus about what happens inside the sphere of influence, which we have to compute. Oh, but then we left saying that if I now want to come back, because probably I want to come back, especially if I have people on that spacecraft, what is the condition that has to occur so that I can now leave the orbit, the red orbit of planet 2, go on another half ellipse that looks identical to the other one. The time of flight is the same. It's just below, if you want, like in that case. And I need to have planet 1 at the apogee. Right? I'm sorry, at the perigee, at the other side. I need to have planet 1 right there. And I said, well, you have to wait. You can't do it right away. You just can't reach planet 2 here and spend no time here and just burn again and come back and actually hope that planet 1 is going to be there. First of all, what's the point of doing that? Why would you go there to Mars and say bye and then come back? But then you're just not going to have the planet there. We said that the new phase angle, we called it phi0 prime, and I think the book has an error there. This should really be a prime, phi0 prime, because that's what actually is done in calculation. Has to be, I said, this needs to be minus phi final. How do you prove this? Well, the reasoning is should be relatively simple. The time that is spent on the cruise trajectory is exactly the same. So the angles that the two planets are covering on their trajectories are the same. The difference is now that while before I require 2 to be in a certain location at the end of the cruise, here I have to have 1 right there. And 1 has done what before? 1 has covered pi plus this angle here. which according to my definition is a negative value because planet 1 is ahead, well, the same will have to happen when I'm coming back, right? The planet 1 will cover something that measures like phi f in absolute value plus pi, and that's where I hope to meet my spacecraft. So that's why we say, okay, if I'm kicking out spacecraft, the spacecraft from planet 2 attraction right here, don't think that this is exactly the same condition, okay? These are just representations. You can rotate these plots as much as you want, meaning these lines, these line of ups can be like this at 45 degrees. It doesn't really matter. This is just an example to show that now I'm leaving from planet 2. Planet 2 could be here. You can rotate the entire image, okay? So now what is happening, I'm leaving from here. I am going to hit this guy, planet 1, only if it was behind of exactly minus phi f, right? Does it make sense? Planet 1 has to cover the same distance on its circle. Is that clear? And so how do I make sure that that happens? Well, you have to wait. As I said, if you do it here, you can prove it to yourself. Try to do it. You're not going to find planet 1 right there because it's going to take another T12 here. And planet, what is going to happen if you leave right away? Well, planet 1 is going to cover exactly another angle like this. So it's going to be here at pi plus another piece here is definitely not going to be there. You have to wait. And so the wait time is easily computed by saying, okay, I have arrived at planet 2. I'm going to reset the clock right there. That's my new time 0. And so I want my phase angle to be this. And so the new expression for phase angle, if time 0 is now after I have arrived at planet 2, is going to be this, right? Now t is counted from the moment I've reached planet 2. So my initial condition is it's phi f. Okay? Make sense? Remember what I said last time. I said the general equation for the phase angle between the two planets is going to be some initial phase angle plus n2 minus n1 t, deciding when is your time 0. Here I've decided that my time 0 is, this was when I was leaving planet 1. This is now when I have arrived at planet 2. And so I want this one, this phi, to be exactly that, minus phi f. I want to wait for this to happen. So if I do this, this is actually my t wait. It's just the equations we're playing with are just simple equations in time, where there is an angle, phi, there is some initial conditions, plus some constant t. That k in this case is the difference of angular velocities. I'm just resetting the clock. I have arrived at Mars, if that's Mars. Now I want to count how much I have to wait until this happens. This is a plus, by the way. It's not another f, okay? And that's the equation. So if you solve for this, that's pretty simple. You're going to get that t wait is minus 2, the phase angle at the end of when you are at arrival at planet 2, and here you have n2 minus n1. Now the problem with this is what? If you're solving a problem where planet 2 is Mars, so the orbit, the red orbit is bigger, n2 is smaller than n1, denominator is negative. Phi f, I have proven that it's actually negative. So this is going to give me a negative number, right? Negative, negative, plus, minus here. I don't like that. Well, but everything is periodic here. So what you do actually is make sure that the numerator is negative, and you basically add a 2 pi n, where n is an integer. So this is the case where n2 is greater than n1. I'm sorry. It's less than n1. There is a very similar relationship if you're going to if your home planet was the outer planet, which looks more or less the same. You just have plus 2 pi n over same n2 minus n1. In this case, n1 is less than n2. I don't know if you can film this so close to the screen, but these are basically the two relationships you need to keep in mind. This is if you're coming back to the smaller circle. This is if you're coming back to a bigger circle. But the use of this is the following. You have the angular velocity of the planets. You have this, the phase angle after you have arrived at the planet. If you don't like the number you're getting, because it's negative, you can't get a negative number, well, start testing n equals 0, 1, 2, 3, until you get the smallest positive number. That's what you really do. That would be the smallest wait time. You don't want that to be huge, unless your mission around that planet too requires a lot of time, but that is really the idea. So this should really cover the timing of these maneuvers. They are just Hohmann maneuvers from the sun's point of view. There's really nothing special about them. You leave a point on this circle, and you reach another point here. You just have to do it when this phi0 respects that condition, and right here. And this repeats itself every synodic period, which is a long one between Mars and Earth, as we've seen last time. Now, if you have to come back, you need to wait for this to happen. And that's your wait time. And the book has great examples about this. And at this point, really, I hope it's clear that interplanetary trajectories are just understanding the concept of the patch conics. There's nothing new in this chapter in terms of the equations that we are using. Is Hohmann transfers, and we'll see now the elliptical departure on the home planet. There's nothing really special. It's just a use of the things that we've already seen. So I think this is the wait time. Yeah, Mars and Earth, same data as last time. You need to find T12, of course, if you want to take into account the travel time. And a Hohmann transfer between the Earth and Mars is almost a year, well, 258 days. And then if you, this is the power of having an electronic book, right? I don't have to copy all these numbers. If you apply phi final, where is it? Right here. This one, yep, right here. That's what you get in radians, negative, as expected. I'm going to a bigger orbit. And if you then want to compute the wait time until the moment you can actually burn and come back and meet rendezvous with the Earth coming back, I'm applying the first version of this formula where here they're telling you if you set n equals 0, you get a negative number. Not a good thing. With n equals 1, you get a positive wait time, which is a long time. That's how long you have to wait before the planets are in the right configuration and you can come back and hope to meet the home planet. Okay? So if you add all of that together, the t wait and twice the t12, I hope it's clear why it's twice, because I am going and then coming back, you get what I showed you last time, these 2.666 years. Now, we're not going to cover alternative ways to get to Mars, which is of interest these days, because, well, if we have time, we're gonna see a delta V example just to leave the planet, how much fuel it costs you. With an engine that has an impulse, specific impulse of 300 seconds, in one of the examples that your book gives you, you spend 70% of the mass of your spacecraft. So you may not have enough to even come back. So these maneuvers are extremely expensive. You need engines that are powerful enough, but at the same time very efficient, and usually the two things don't go together, as we all know. Or smarter maneuvers, or longer maneuvers. So alternative to Hohmann transfers, of course, you can have a continuous electric engine that pushes you all the time, like what Patrick has showed in his lecture. Solar radiation pressure is a very small acceleration, but if you keep it on all the time, you get pretty high velocities over a long time, though. So it's always a trade-off of time and how much mass you can really have on your spacecraft. So let's now talk about that. That's exactly what I need to do, because we know how to deal with these outside of the sphere of influence. That's what we have done. But we need to define what this sphere of influence is, because we need to prove that it's very small compared to the distances between planets and the sun. Okay? So if I have the sun here, and my planet somewhere here, ms is mass of the sun, mp is mass of the planet, and let's say that my spacecraft is somewhere up here and it's just simple m, and I'm going to give names to these vectors, which are, let's see, I have, of course, little r is from planet to the satellite, big rs is the vector that goes from the sun to the satellite, and I think simple r is what I have here for planet, well, from sun to the planet. So I want to basically define this imaginary sphere around the planet where basically I can say, okay, after this distance, the sun is really taking over. The acceleration that is due to the attraction from Earth it becomes negligible. I don't care about that anymore. Okay, so the force, let me give some forces here. Force P, it would be the force that the planet is exerting on the satellite, which is the one that we have seen so far. Gm, mass of the planet, over r cubed, little r vector. We usually divide by the mass of the spacecraft, and we get the usual, this will be your mu, right? This is your mu of the planet. Okay, then we have the force that the sun exerts on the spacecraft, which is something similar, except now I have mass of the sun here, and this is rs cubed rs vector. And then I have what I'm calling here, your book may use a different name probably for these vectors, doesn't matter. What did I call this? This is the force that the sun is exerting on the planet. Otherwise the planet would just go straight, right? mp ms over r cubed r. So I want to use these two vectors, I want to involve these two vectors to get r double dot at some point. But let's see a few things. I can switch these off for now and then bring it back. Oh, not the light. Okay. So there's a few things that we can look at. The first one is how the spacecraft is moving relative to the sun. And that equation is going to be mrs double dot, which is equal to Fs plus Fp. Those are the forces, right? If you divide, of course, by the mass, you get the acceleration here, and that will look like 1 over m minus g m ms rs cubed rs vector plus, go down here, 1 over m minus g m mp over little r cubed r vector. You can do your simplifications, of course. The mass goes away everywhere here. And you can call this first term, let's call it the acceleration that is due to the sun. And the second one, I'm going to call it the perturbation due to the planet. So I'm basically saying I care about what the spacecraft is doing from the sun's point of view. So if I am sitting on the sun, this is the force that I am as the sun exerting, the acceleration, this first term here. S is not spacecraft, I'm sorry, it's sun. Spacecraft doesn't have anything. Where you see values, little r without any subscript, and little m without any subscript, that's our spacecraft, okay? P is the planet, S is the sun. So that is what the sun is doing to the spacecraft, and we see the planet as a perturbation. I can do that, right? I can call whatever I want these two terms. And I'm going to define the following ratio that I'm going to save here. The ratio of the absolute values of those two, perturbation due to the planet over acceleration due to the sun, it's g, let's see, mp over r squared, right? This one? Remember, this is a vector, so if I want the norm of this is r, and this becomes an r squared. And this is divided by, let's see, the other one, gms rs squared, where simplified you get mp over ms rs over little r squared, and we just leave it there. I use that. Then, so this allowed me also to find an equation for, remember, for this vector, big R s double dot. I'm going to use it later on. Now if I look at the planet with respect to the sun, or relative to the sun, I get something similar, right? The equation of motion now is m planet big R without any superscript double dot, it's, what is this? It would be, what did I call that? FSP, right? And let's have it for now, this would be minus the force that FP, which will be the force that the planet is exerting on the spacecraft. This will be the force that the spacecraft is exerting on the planet, which is kind of ridiculous when you divide by the mass, but let's leave it there. And so, same thing, I'm going to divide by the mass. This is what you get. You get G, same procedure, M, R cubed, R vector, minus G, MS, R, big R cubed, R vector, right? Look at those. The FSP is down there. I have changed, it's this one, right? Divide by the mass of the planet. That's what you get. Minus stays there. The other one I've changed the sign. It's the top one. Divide by the mass of the planet. That's what you get. And so the difference now, I really don't want to erase that. Now finally I can look at this one. The little r double dot, which is rs double dot minus r double dot, and I have an equation for both, right? This is the equation that gives me rs double dot, and this is the equation that gives me r double dot. Is going to look like this, minus g mp over r cubed. I'm going to just show why it looks like this in a second. Cubed rs minus rs over r cubed r vector. This is actually a square bracket. So I'm just taking those two and subtracting them. Let's see. Rs double dot is this one. Let me rewrite it, just removing all the simplifications. It's minus g ms rs over rs cubed, and then we had minus g mass of the planet r cubed r. So I recognize this term, it's right here. This term is right here, right? So those are there. And then I am subtracting these two pieces. And here is the first one. It gives me this little m over mp. We see that? Remember, I'm subtracting, so the minus goes outside and there is a plus here. Because the g, m, r cubed, r, it's all in common, except the little m is different, so I'm divided by mp right there. And this term is here. It's just one additional step that I've skipped. Just collecting, what I'm doing is subtracting these two vectors. Again, it's this vector as it is minus this vector as it is. The only thing that I've done is I've collected at some point this term gmp over r cubed r and gms over rs cubed. And that's all. That's it. It's nothing special. Okay. Then, one more step. Well, remember that r is also rs minus r. I have it right here, right? If you substitute in here, you get minus g mp over r cubed. Well, the first term really doesn't change much. I'm going to have to simplify a few things, as usual. Okay, little r plus 1 minus Okay. What is the step between this and this? I take everywhere I see rs, I substitute little r plus big R. You get that. But you can basically forget about that expression if you want, because we're going to simplify it. So all we need to keep in mind, there is this ratio here, and I'm going to compute another ratio, and I'm going to compare the two. That's all that really matters. But these are all the usual vectors, accelerations, vectors, time derivatives that we have computed so far. So now, what can I remove there? Well, the mass of the spacecraft is probably going to be much less than the mass of the planet, right? Agree? And then, what about distances? What do you think? What I want to compute is this sphere of influence, which I don't know how big it is, but my feeling is it's probably going to be pretty small compared to the distance between planet and the sun, right? That's my idea. And so, can I say this? I think I can. In other words, if I am inside this sphere of influence, meaning I still am looking at the motion of the object from the point of view of the planet, because I'm not that far away, I'm not in a heliocentric orbit, this distance here, this vector little r, which we have dealt with for a long time at this point, is probably going to be very small. Imagine yourself again sitting you're sitting on the sun and you're looking at the planet Earth. Any of the satellites around the planet Earth, you're not going to be able to even see them. They can be even at high orbits, geostationary orbits. These little r's are always going to be very small compared to this distance. And so we can approximate really the distance between sun and satellite as the distance between sun and the planet itself. Okay? So if I do all these approximations in there, what do I get? I get that basically my r double dot is going to collapse into, let's see, minus g m planet little r cubed r, no surprise. MS, you have any questions? So everywhere you see rs, put just r, and everywhere you see, for example, this ratio here, this goes to 0. Can't neglect that. And so if this goes to 0, I'm left with this first term minus gmp over r cubed r, that's all. And then this second one, if rs and r are the same, this 1 minus 1, it's 0, and that's what I have. Did I forget something? Yeah. This is not big r, this is little r. Makes sense. You see that? So, in other words, this goes away, and this whole piece goes away. Because I want to compute this sphere of influence, I have to assume that I am still close to the planet. I'm not flying away from the planet yet. So we do the same thing that we have done there. Now we call these two accelerations acceleration due to the planet, and now this is perturbation due to the sun. We see that? This is what the sun is doing to my object, to my satellite, and this is what the Earth is doing to my satellite. There's nothing new here. We have seen these so many times at this point. And so the ratio that we are interested in now is, again, it's a perturbation. I can put it here. PS over AP, which is going to be, if you simplify like we've done there, MS over MP little r over big R cubed. So I put myself in the case where the satellite is flying with respect to the sun, and I find this relationship here where the sun is the main body and the planet is a perturbation. Here I'm doing the opposite. The sun is a perturbation, the planet is the main body. So I want to merge these two to find the limit where what? What would you set up with those two relationships? So you have these two ratios. How would you define your sphere of influence? What would be a meaningful way to do it? What do you think? Which one has to win if you want to be inside the sphere of influence? Yeah, right. So how about these needs to be less than these, right? Perturbation of the sun over the acceleration of the planet has to be less than this. The planet has to win, so its perturbation is bigger. So if you do that, PS over AP less than PP over AS, this is going to look like this. It's mass of the sun over mass of the planet. Distance to the satellite from the planet over distance between sun and planet cubed has to be less than that equation there, MP over MS. Now I have Am I still calling it RS? I think I can just call it R because that's what I have assumed, right? So R over little r squared. And so if I keep going with this, so of course when they are equal, that would be my sphere of influence. That's the definition of sphere of influence. If that relationship holds like that with the less than, you are inside the sphere of influence. When you are at the equal, you get the sphere of influence. So let's manipulate that. What do we get? I'm going to bring everything on that side in terms of radiuses. Okay. MP over ms squared, right? And so finally, my radius of the sphere of influence over the distance to the sun is defined pretty much as mp over m sun, this was sun, to the 2 over 5. That's what it is. I hope. Yeah, that's what it is. So all I've done is just a bunch of calculations with time derivatives of vectors, nothing special. With the forces, that are all Keplerian, by the way. And by defining those ratios and deciding that this is the condition for being inside the sphere of influence, you get this expression right here. And so what happens is you definitely have the masses of the planets and the sun, right? Depending on the planet, you can compute this. This will be the distance of your planet from the sun. That's involved as well. But for example, for the Earth, I believe, if you go in your book, the sphere of influence of the Earth is about 150, 145, something like that, radius of the planet itself. So you have to be 145 times the radius of the Earth away from the Earth to say that you are at the sphere of influence edge. And after that, you're going and fly around the sun. Of course, this is not true. I mean, the sun and the planet always affect you, but this is, again, patched conics. I want to divide the problem into heliocentric, and then I'm going to focus on what happens inside the sphere of influence. The moment I'm outside of the sphere of influence, it's what we have just done. Okay? You don't even see the orbits of the satellites around those planets. They just disappear. They become so small that you don't see them. Why so small? I think the distance, for example, this one, that would be the distance. So this would be Earth to Sun. I think I wrote it down here. Yeah. It's about 23,460 times the radius of the Earth. So yeah, this is definitely bigger than that. Agree on that? Radius of the Earth is 6,378, about that, kilometers. So to make sure that we can use this method of forgetting about what happens around the planet once you are outside the sphere of influence, it is mandatory that this sphere of influence that we define has to be small with respect to the distances that are involved. So that at some point you can really see things happening just from the sun's perspective. Make sense? So you can basically neglect the maneuvers you're doing at the vicinity of the planet from the sun's point of view. You're sitting on the sun, you don't even see that someone is turning on an engine and is going on a hyperbolic flight. You don't see all of that happening because it's so small. And that's exactly what you need to compare. 23,460 compared to 145. It is definitely negligible. I mean, that's what we assume. For other planets, the relationship may be different, but especially as you go closer to the sun. But for us, that's what we have. Questions on this? Why do I need to go through this painful stuff? Because this is the transition to seeing what happens now in the vicinity of the planet. Because what gives me now those delta V's, Hohmann delta V's, that I assume I can have leaving planet 1 and then I arrive at planet 2 and I probably have to speed up again. But that's from the sun's point of view. What is happening in the vicinity of the planet is a different story. We said that we need to leave the planet, and that means going on a hyperbolic path with respect to the planet itself. Can I erase this? And so this is the connection point. Outside the sphere of influence, you do what we have done. Inside the sphere of influence, you do what I'm going to do now. You compute the delta V's in a kind of a strange way. Let's see if I can. For this part, the book has beautiful pictures that I want to show. So with all different colors. The moment I find them, I'll show you. Yes, here it is. Okay, so say that I'm leaving planet 1, and next time we'll do arriving at planet 2. Nothing special between the two. There's really nothing different. But so, this is what you do. We said the delta V that you need at planet 1 to leave planet 1, right? We said that was square root of mu sun over R1 square root 2R2 over R1 plus R2. This is all coming from the energy equations, just done with respect to the sun. There's nothing special. So what is actually this? This is the V infinity. Because with respect to the sun, you are going to fly, if you're going on a hyperbolic trajectory, you're going to fly at a velocity which is V of your home planet, V1, plus the velocity relative to the planet, V infinity. Right? Everything that we have done up to this point, remember in the ECI, if we're talking about Earth's centered orbits, everything we have done where we talked about these little R vector and V vectors, these are all relative to the planet. The planet is going around the sun. So now we have to add that velocity of the planet around the sun, whatever that is, V1, right there, if we want to know how the satellite is moving with respect to the sun. And that's what we define at the edge of the sphere of influence. The moment you reach that imaginary edge of the sphere of influence, you are under the influence of the sun. So what you want to make sure is basically the following, that you go on some kind of hyperbolic path, and you want to make sure that your V infinity is the correct value, so that is giving you this. So this is the patching between the conics, really. It's this point right here. What I've done up to this point is just Oman transfers between a circle and a bigger circle. And you can compute the delta V's, right? And this is one of them. This is to leave the smaller circle and go on the big one, right? And go on the cruise trajectory. So this is the first delta V. Well, how do I connect that to what happens inside the sphere of influence? Here it is. You need to make sure that you're leaving the planet on a hyperbolic path that has exactly this V infinity. This is a number. If you go into Mars, this is the radius of the Earth around the sun, right? R1, this is Earth, Sun, and R2 is Mars, Sun. So everything here is known. Mu of the sun is a constant. You want to go there on a Hohmann transfer, this is how much speed you need to have above the velocity of the Earth, on top of that. Okay? So how do you make sure of that? So the V infinity is basically a given, okay? So the steps are the following. I'm just going to give you the steps here because I am not using anything that we have not seen before. Remember when we finished the chapter about Keplerian orbits and there was that summarizing table, kind of table at the end with a bunch of formulas for the circle, parabola, etc. That's exactly what you use here. There's nothing special. It's just that now someone is giving you the V infinity. You're solving the problem in a different way. You are given that value. So let me see. Well, that would be the first step, right? The delta V. If you want to solve for what you need to do to leave the planet, this is step 1. Compute the delta V Hohmann and know that that has to be your V infinity. We need to make sure about a few things here. We need to make sure that that V infinity is parallel to V1. Otherwise, can't call it an impulsive maneuver, right? The delta V's you give for Hohmann transfers are all pumping maneuvers. There's no change of vector direction. You either speed it up or slow it down. Okay? So that I need to make sure, and we'll do it. But then what is really happening in practice? From the sun's perspective, you've done something that gives you a delta V, and you leave the orbit of planet 1. From the planet's perspective, though, you're probably on a circular parking orbit or something like that around the planet. You have reached some altitude, and then when you're ready, when the phi 0 is met, you actually burn an engine and go into a hyperbolic path, right? So this is the difference now, that the delta V is not really occurring at the sphere of influence. You don't do anything at the sphere of influence. You do it here. Make sense? Unless you're launching from the planet already on a hyperbolic path, which I don't think anyone does. So you're flying on, and that's what we're going to assume. Let's say that you're flying on a circular orbit of some radius r, okay? And when the time is right, you transfer to the to the hyperbolic path that will go to infinity. So what is the next step? Well, the next step is characterizing that hyperbolic path, because I need to make sure that this angle is correct, beta. So I need to make sure that I fire the engine right here, not here or somewhere else, because my V infinity has to be parallel to V1. So I need to make sure about beta. And so my inputs here are this V infinity, and 2, the other input is the radius of, let's assume again I'm leaving from a circular orbit, of the parking orbit. Doesn't have to be circular, but this makes things a little easier. And let's call this R. I'm going to call it RP. But that's, yeah, I think that's fine. So what do I do with this now? Do you have any memories about these values involved? For example, that angle theta, which is between the angle between the line of apse and the asymptotes of the hyperbola. Remember what that was? Maybe? Something like this. So, with these inputs, this is known. So basically these are given. This is the heliocentric common transfer is giving me this. You need to have this. And this is where I am before I go on the hyperbolic path. I definitely want to find the eccentricity, for example. That would be a good idea. So known formulas that you can use are the following. And again, I'm not going to really bother rederiving them because we have done it. So this is mu of planet 1 over 1 plus e. So this will be the perigee of my hyperbola, right? And I know that this has to be, because cosine of theta is 1, okay? So this is the standard Keplerian orbit, parametric orbit formula, where cosine of 1, I set it to be 1, so that I am a perigee. And I want that to be RP. Because I was on this circular parking orbit, and at some point I turn on the engine, and if I go on a hyperbolic path, the only intersection between the circle and the hyperbola is the perigee of the hyperbola. Then you're just going away. Okay? So that is a known fact right there. And then there is another formula that we can use, which is this other one. And again, it's in your tables, that connects the angular momentum with eccentricity of the infinity. So if you combine these two together, you can find E. So basically, RP is given, V infinity is given. Substitute H in here, for example. Do a little bit of algebra, and this is your eccentricity. Which is using the inputs. I was given the V infinity. I was given the initial, basically the perigee of that hyperbola. It's set, because that's where I am. I am living from there. Whatever I do, I have to turn an engine, and that will be my perigee of the hyperbola. So those are the inputs right here. This is mu of the home planet, and this is the eccentricity that you need, that you're going to provide on that trajectory. Okay? Make sense? Yes? No? Now, what am I going with this? Well, first of all, once I have the eccentricity, here is a first piece of information that you need to respect this. You need to make sure that the burn you provide has to be such that this angle beta is respected. You know the direction of the velocity of the planet. Well, you want to be at an angle beta on your circle, parking circle, when you turn on your engine, your impulsive maneuver, and that's your beta value. So that's an important calculation you have to do. Because again, you can't just burn at any point on this parking trajectory. If you burn here, it doesn't matter if the delta V is right. Your hyperbola is probably going to be here. And the V infinity is going to point this way. And that is a vector that adds up to V1. And it's probably not going to give you the right Hohmann initial velocity, right? Yes?
Is the reason for going straight into the direction of V1 just for efficiency?
Well, you're going to have, so again, this is an approximation. But if you assume that it's valid, at the exit of the sphere of influence, your velocity vector with respect to the sun, so I don't know what I'm going to call this, spacecraft with respect to the sun, SS, it's going to be V of the planet, which is V1 plus v infinity as vectors. This is the velocity of the satellite with respect to the planet. This is the velocity of the planet. If these two are not parallel, you're exiting the sphere of influence with the velocity with respect to the sun. So while this is the sun, and you wanted to be right here with this velocity so that you are on a perfect ellipse that is going to meet Mars down here, if that's not your v, it's something like this, that's not the trajectory you're going to get. You're not going on a Hohmann transfer. And that's what we are doing here. I'm assuming that from the sun's perspective, I want a Hohmann transfer. At the arrival, by the way, which I'm not going to be able to do today, but at the arrival, well, actually, let's forget about the arrival. But say that you're coming back, and in coming back, you have to slow down at some point. So this is speeding up. This is adding v infinity. You could burn, let's see, here, and have the exit here, and that v infinity is going to reduce your velocity with respect to the sun. It's still going to be this, but the difference is that while these v2, v1, and v infinity, they pump in the same direction, if you exit somewhere else in the sphere of influence, you may actually reduce the velocity with respect to the sun, which you may need to do in some cases, like coming back. Make sense? So basically the idea of the patched conics is, from the sun's perspective, you know the velocities you need to have as you leave a planet and you arrive on the other planet. Once you're given those conditions right here, you call those v infinities, and then you enter the sphere of influence and you make sure that those v infinities are met and they are as vectors pointing in the right direction. And again, if you do Hohmann, you just want to be with the velocity of the planets. Nothing, no angles between those. Make sense? Okay, so there is really just one more step, more or less. What? Okay, that's the angle. Can I erase this? Yes. Now, what is the velocity at Perigee for the hyperbolic path? Well, since it's Perigee, you can just directly do h over rp, right? Velocity and position vector are at 90 degrees with each other. And if you do your calculations, you're going to see that it's v infinity. Again, all these things are in the book. If you want to see the details of the things that it looks like I'm skipping, but I'm really not that much, they're there. But there is nothing new. It's all Keplerian ideal conics. So this is the velocity you need to have at that point P at the perigee to be on the correct hyperbolic path. So your real delta V, the actual maneuver that you are going to do, is not up there at the end of the, at the edge of the sphere of influence. It's actually at the perigee, and the delta V, it's simply what? Is this minus the velocity on the circular orbit, v infinity squared plus 2 mu1 over rp minus square root of mu1 over rp itself. Because this is where I was before on the parking circular orbit. That was my velocity. This is what I have to go on the hyperbolic path. And you have everything. Now you know how much delta V you need to give at that point P, and you know where that point P is because it's given by this angle beta. It's really just playing with the vectors and make sure that they align correctly. And again, I really like this chapter on the book, so that's why I'm using it that much, kind of abusing it probably. But the examples that they have are pretty clear, and the images in particular. So this is exactly doing what we said. If you have a spacecraft that has to go to Mars on that Hohmann transfer we talked about for a while now, and you're starting from a parking orbit of 300 kilometers, circular. Again, this is the V infinity, just that now R2 becomes R of Mars with respect, around the Sun, and R1 is R of the Earth. That's your V infinity. You need to leave the planet. You need to be flying 2.9, almost 3 kilometers per second faster than the Earth. And the Earth is flying pretty fast around the Sun. I don't know exactly what the number is. We can figure it out. But that is what you're adding on top of the velocity. Oh, here it is. No, forget about it. No, this is not it. This is the V infinity you need to have. This is the circular velocity on the parking orbit. Makes sense, about 7 kilometers, almost 8. And this will be the delta V you need to give according to this expression right here. Okay? I don't know if they do, if they go through the pain of actually computing the eccentricity and the beta angle. I don't think they do that, because all they are doing here is trying to basically impress us by how much fuel you need to have. So the actual delta V is right here. So this is what you are doing on that parking orbit. Burn an engine, go on the hyperbolic path. It's 3.6 kilometers per second with an engine of, remember this expression here? With an engine that has an ISP of 300 seconds, which is a realistic one, you are using 70% of your mass just to go away. So it's a big deal. You may not be able to come back. In this case, I don't think you can come back. If you're going to do comparable maneuvers at the other side, you don't have another 70%. We don't have 140% fuel usually, right? So I think we're done for today, but we'll finish these. We'll do the arrival and maybe fly by. And let me know if you have any questions. In the meantime.